The main question we'll be answering is, how does light behave when it strikes the interface between two media with different refractive indices? We will answer this question in three different ways using the different models of light we have encountered, namely the ray model, the scalar wave model, and the vectorial wave model. We will see how these different models lead to the same conclusions on the one hand, but also how the more complicated models allow us to derive new results. So let's start with the simplest model of light, namely the ray model. When a ray of light strikes the interface at an incident angle of theta I, it can be reflected at an angle of reflection theta r, or it can be transmitted at an angle theta t. The angle at which the light is reflected is described by the law of reflection, which says that the angle of reflection is the same as the angle of incidence. If the light is transmitted and refracted, the angle of refraction can be found using Snell's law. Let's look at the implications of Snell's law in more detail. If the refractive index of the second medium is higher than the refractive index of the first medium, then the transmitted angle must be smaller than the incident angle, so the transmitted ray will be bent towards the normal. If the first medium has the higher refractive index, then the transmitted ray will bend away from the normal. The larger the angle of incidence is, the larger the angle of transmission is. At some point, the incident angle is so large that the transmitted ray will be parallel to the interface. The incident angle for which this happens is called the critical angle. Using Snell's law, we can find an expression for the critical angle by setting the angle of transmission equal to 90 degrees. If we increase the angle of incidence beyond the critical angle, then the light cannot be transmitted, so instead it is reflected. This phenomenon is called total internal reflection, which is important in, for example, optical fiber cables. So far, we've just stated the laws of reflection and refraction and looked at their implications. But why should these be the laws that govern the behavior of light at an interface? It turns out that both laws can be derived from a more fundamental principle, namely Fermat's principle. Simply put, it states that when light travels between 2 points, it will take the path that takes the least amount of time. So let's see how we can use this principle to derive Snell's law. Suppose we have two media with different refractive indices n1 and n2, and we want to see how light travels from a point A in the first medium to a point B in the second medium. Because the media have different refractive indices, the light travels at different speeds in the two media. So now the question is, at which point x does the ray have to hit the interface so that the total travel time from A to B is minimal? To find this point, we write the total travel time as a function of x. The total time is equal to the distance traveled in medium 1 divided by the speed in medium 1 plus the distance traveled in medium 2 divided by the speed in medium 2. If we multiply both sides by c, we get an expression that involves the refractive indices multiplied by the geometric distances, which is referred to as the optical path length. In order to write this expression more explicitly as a function of x, let's define a few quantities. Let L be the horizontal distance between points A and B, so that the distance between point A and point x is x, and the distance between point x and point B is L minus x. Let the vertical distances from point x to point A be HA, and the vertical distance from point x to point B be HB. Now we can write the expression for CT more explicitly as a function of x using Pythagoras' theorem. Since we want to find the point x for which the total travel time is minimized, we take the derivative of CT with respect to x and we will set it equal to 0. So if we write down the expression for the derivative, we see that we can write it in terms of the sine of the incident angle and the sine of the transmitted angle. And if we set this expression equal to 0, we can rearrange it to find Snell's law. Now let's look at the law of reflection, so we have 2 points A and B at the same side of a mirror. If we were to find the quickest path between the 2 points, the solution would be simple. The light would go in a straight line from point A to point B. So how could we derive the law of reflection from Fermat's principle? The problem is that our current formulation of Fermat's principle is too simplified. If we were to be more precise, Fermat's principle doesn't just state that light takes the quickest path, but rather that light takes the path for which the optical path length is an extremum. This means that the travel time could be a global minimum, but it could also be a local minimum, or even a local maximum. So now it should be clear how we can use Fermat's principle to derive the law of reflection. Light has to go from point A to point B via a point X on the mirror, so that its travel time is a local minimum. To find this point X, we again write the expression for the optical path length, and we define L as the horizontal distance between points A and B, and HA and HB as the vertical distances between X and A and B respectively. We can write down the optical path length explicitly as a function of X, take the derivative with respect to X, write it as a function of the incident angle and the reflected angle, and set it equal to 0 to find the law of reflection. So we've seen that we can derive the laws of refraction and reflection using Fermat's principle of least time. But why should this principle work? How would light know which path has an optical path length which is a local minimum? To answer this question, we have to consider the wave model of light, Huygens principle, and constructive and destructive interference. If we have a point source at point A, then it will emit spherical waves. In terms of ray optics, it means that point A emits rays in all directions, and that these rays are coherent with each other, so their phase differences matter. When a ray hits the mirror at a certain point, that point will act as another point source according to Huygens' principle, so it will again emit rays in all directions. So basically there are many paths that the light takes at once to go from point A to point B. So why is it that for a certain point X the contribution would be larger than for other points? As we will see, the answer lies in constructive and destructive interference. We can plot the optical path length as a function of X. For a certain X, the optical path length is a local minimum, and according to Fermat's principle, this X defines the path that the light would take. To see why this is the case, recall that as light propagates, it undergoes a phase shift, and this phase shift is proportional to the optical path length. To find the total field in point B, we have to add all the rays that are emitted from point A together, and all these rays undergo different phase shifts, depending on the point of reflection X. When we visually add all these different phase factors together in the complex plane, we see that when the optical path length varies rapidly as a function of X, the rays interfere destructively, so they barely contribute to the total field in B. However, near the local minimum where the optical path length is approximately constant, the rays interfere constructively, thus leading to a large contribution to the total field in B. And so we see that Fermat's principle works because the rays that travel along paths which have a minimal optical path length undergo approximately the same phase shift during propagation, so they act constructively, while rays traveling along other paths interfere destructively. Now let's see how we can use this principle to design focusing mirrors. Suppose we want to focus all the light emitted from a point A into a single focal point B using a mirror. What shape should the mirror have? The mirror should be shaped such that all paths from A to B via any point X on the mirror should have the same length, so that all the rays arriving at B have accumulated the same phase and therefore interfere constructively. So AX plus BX should equal the same constant for all X. This equation describes an ellipse with focal points A and B, so in order to focus light from point A in point B or vice versa, we require an elliptical mirror. Now let's say we have an incoming bundle of parallel rays which we want to focus with the mirror into a single point B. What this means is that for each point X on the mirror, all rays that go via point X to point B should have the same phase so that they interfere constructively. Since the bundle consists of rays going parallel to each other, we know that for any line L perpendicular to the bundle, all rays have the same phase when they pass through that line. Since we want all the rays that travel via point X to point B also to have the same phase, we can require that the distance from B to X should be the same as the distance from point X to line L. This equation describes a parabola, so we find that if we want to focus a parallel bundle of rays into a single focal point, we require a parabolic mirror. Conversely, if you were to put a point source in the focal point of the parabolic mirror, the mirror would convert it into a parallel bundle of rays. Parabolic reflectors are commonly used in, for example, satellite dishes, spotlights, or parabolic microphones, which are used to pick up sounds from one particular direction. Now that we have explored how we can use the ray model to describe the behavior of light at an interface, let's now see what other results we can derive using the scalar wave model of light. Suppose we again have an interface between two media with refractive indices n1 and n2. we can write the incident plane wave as its complex amplitude ui multiplied by a phase vector e to the power I n1 ki dot r, where ki is the incident wave vector and r is the position vector. More explicitly, if we assume the incident wave vector lies in the xz plane, we can write ki dot r as kxi x plus kzi z. Similarly, we can define the reflected wave and transmitted wave, which have wave vectors kr and kt respectively. Note that in this convention kzi and kct are negative because the waves propagate in the negative z direction. In order to derive the law of reflection and Snell's law of refraction, we assume that the total field should be continuous at the interface, which is at z is equal to 0. One thing this means intuitively is that the wavefronts of the incident, reflected and transmitted waves should connect at the interface. Mathematically, it means that the complex exponential should be the same, so n1 times kxi is equal to n1 kxr is equal to n2 kxt. In other words, the tangential component of the k-vector should be continuous at the interface. Let's see what this implies for the reflected field. We see that the incident kx should be equal to the reflected kx. By drawing the incident and reflected kx and kc in the diagram, we can see that the equation can be rewritten as k sine theta I is equal to k sine theta r, where k denotes the length of the wave vector in vacuum. Note that we use the wave vector in vacuum and not in a medium with refractive index n1, because that has already been taken into account in the complex exponential. We now have an equation that says that the angle of reflection is equal to the angle of incidence, which is once again the law of reflection. Now let's look at how the transmitted wave vector is related to the incident wave vector. From the continuity of the tangential component of k, it follows that n1 kxi is equal to n2 kxt. Once again, we can write kx as k sine theta, where k denotes the length of the wave vector in vacuum. Cancelling out the k's on both sides gives us the equation n1 sine theta I is equal to n2 sine theta t, which is Snell's law. So we have seen that by requiring that the field is continuous at the interface, we can derive the laws of reflection and refraction. So what can we derive with the scalar wave model that we couldn't derive using the ray model? Recall that in the ray model we could define a critical angle at which the transmitted ray is parallel to the interface. We said that if the incident angle is larger than the critical angle, no transmission can take place, and the ray is totally internally reflected. But let's see what happens when we analyze the situation using continuity of the tangential component of the k-vector. We saw that we could write this equation in terms of sine theta I and sine theta t. At the critical angle, theta t is equal to 90 degrees, so in that case n1 kxi is equal to n2k. So if n1 kxi is larger than n2k, the incident angle is larger than the critical angle. What will happen to the transmitted wave vector? We can find from the continuity of the tangential component of the k-vector that if the incident angle is larger than the critical angle, the tangential component of the transmitted wave vector is larger than k. From the fact that the transmitted wave vector should have length k, we find that its z component must therefore be imaginary. If we put an imaginary kz in the expression for the transmitted plane wave, we find that while the wave propagates along the interface in the x direction, it decays exponentially in the negative z direction if we choose the correct sign for the square root. Thus, when the incident angle is larger than the critical angle, the transmitted wave will be an evanescent wave. This means that as opposed to what we predicted using the ray model, there will be some non-zero field at the other side of the interface when total internal reflection occurs. Is there a way to physically demonstrate the existence of this evanescent field? One way to demonstrate this is by putting a second medium of refractive index n1 some small distance behind the interface. When the evanescent wave hits the second interface, it gets converted back into a propagating wave, so even though the incident wave hits the first interface at an angle larger than the critical angle, it still gets transmitted. This phenomenon is called frustrated total internal reflection, which is very similar to quantum tunneling. By changing the size of the gap, we can change the amount of light that is transmitted. The transmission coefficient depends approximately exponentially on the gap size, as one would expect in the case of an exponentially decaying evanescent wave. So we've now seen how using the scalar wave model allows us to derive the existence of evanescent waves and frustrated total eternal reflection, which we couldn't derive using the ray model of light. Now let's see what we can derive using the full vectorial electromagnetic wave model of light. We're going to derive the reflection and transmission coefficients, which we will see are dependent on the polarization and the incident angle of the incoming light. To derive these coefficients, we'll do the following steps. First, we'll derive from Maxwell's equations that the tangential components of the electric and magnetic field should be continuous at the interface. Then, we'll derive the relation between the electric and the magnetic field, also using Maxwell's equations. After that, we'll define two orthogonal states of polarization, which are called S and P polarization, also called transverse electric and transverse magnetic polarization. Then we can calculate the reflection and transmission coefficients for both S and P polarization using the continuity equations and the relation between the electric and magnetic field. The expressions for the reflection and transmission coefficients are also called the Fresnel equations. We can use these equations to find the Brewster angle, which is the angle of incidence for which unpolarized light can be converted to polarized light. To demonstrate the continuity of the tangential component of the electric field at the interface, we start with one of Maxwell's equations known as Faraday's law, which relates the curl of the electric field to the rate of change of the magnetic field. If we integrate both sides of the equation over a certain area, we can apply Stokes' theorem to the left-hand side of the equation to write the surface integral as a line integral. Now let's take the surface of integration to be a narrow rectangle enclosing the interface. For the left-hand side of the equation, we're interested in the electric field along the boundary of the area, and for the right-hand side of the equation, we're interested in the magnetic field that goes through the area. If we make the loop tighter and tighter so that the area goes to zero, then the right-hand side of the equation vanishes. To rewrite the left-hand side of the equation, we can decompose the electric field in a perpendicular component and a parallel component, and we can see that we can write the line integral as an integral of the difference between the tangential electric fields at either side of the interface. Since this integral has to be zero for any arbitrary interval ab, we can conclude that the integrand must be zero, so it follows that the tangential component of the electric field is continuous across the interface. To demonstrate that under certain conditions the same holds for the tangential component of the magnetic field, we take the Maxwell's equation, known as Ampere's law, note how it's similar to Faraday's law, and conclude that if the two media are non-magnetic and if there are no surface currents, the tangential component of the magnetic field must by the same reasoning be continuous across the interface. And so we find that the tangential component of the electric and magnetic fields should be continuous across the interface, which we will later use to derive the reflection and transmission coefficients. Now let's see how the electric field and magnetic field are related to each other. Recall the plane wave solution for the electric field. We have a vector A that contains the complex amplitudes of the x, y, and z components of the electric field. We have a complex exponential describing a plane wave propagating in the direction of the wave vector k, and we have a complex exponential describing the time dependence. Recall that from the first Maxwell's equation, which says that the divergence of the electric field is zero, it follows that the electric field must oscillate perpendicularly to the direction of propagation. To see how the magnetic field is related to the electric field, we once again use Faraday's law. If we plug in our expression for the electric field, we find an expression for the time derivative of the magnetic field. If we then integrate with respect to time, we find an expression for the magnetic field itself, and we see that we can rewrite this as a cross product of the wave vector with the electric field, multiplied by a factor that depends on the refractive index of the medium the wave is propagating in. In fact, we can show that the magnitude of the magnetic field is the same as the magnitude of the electric field, divided by the propagation speed of the wave in that medium. To see what this means visually, we can imagine a plane wave propagating in the direction of a wave vector k, so the electric field must oscillate in some direction perpendicular to k. The magnetic field must then oscillate perpendicularly to both E and k, in phase with the electric field and with some amplitude that depends on the propagation speed of the wave. Now that we've seen how the electric and magnetic fields are related to each other, let's define two orthogonal states of polarization, S and P polarization. Let's say a plane wave with wave vector k hits an interface at a certain incident angle. We know that the electric field must oscillate perpendicularly to k, so we can draw a vector E perpendicularly to k to describe one possible electric field. This state of polarization, where the electric field vector lies in the plane of incidence which is spanned by the wave vector and surface normal of the interface, is called P-polarization. If we define an xz coordinate system and an incident angle theta, then we can define a unit vector that indicates the direction of P-polarization. Another direction in which the electric field can be polarized is perpendicular to the plane of incidence, which in this case would be in the y direction. This state of polarization is called S-polarization, and again we can define a unit vector indicating this direction of polarization. S-polarization is also called transverse electric polarization or TE polarization because the electric field points along the direction of the interface, and similarly, P-polarization is also called transverse magnetic or TM polarization because the magnetic field points along the direction of the interface. In general, any state of polarization can be written as a linear combination of S-polarized and P-polarized light. At this point, we have all the equations and definitions required to derive the reflection and transmission coefficients of an interface. We're going to derive the reflection and transmission coefficients for S and P polarization separately. Let's start with S polarization. We have some incident wave vector Ki, electric field Ei, which is polarized along the interface and which hits the interface at an angle of incidence theta I. Similarly, we can define the reflected wave vector Kr with electric field Er and a transmitted wave vector Kt and transmitted electric field Et. Notice that all these electric fields are tangential to the interface, so from the continuity of the tangential component of the electric field, it follows that the amplitudes of the incident and the reflected field added together should equal the amplitude of the transmitted field. We also know that the tangential component of the magnetic field should be continuous across the interface, but first we need to find an expression for the magnetic field. Recall the expression we found before using Faraday's law, which expresses the magnetic field in terms of the electric field and the wave vector. We can define the electric field vectors for the incident, reflected, and transmitted waves, and similarly, we can write down the normalized wave vectors for the incident, reflected, and transmitted waves. If we plug in these expressions in the equation for the magnetic field, we pick out the tangential component, so the x component, and we write down the equation for the continuity of the tangential component of the magnetic field. Now we have two continuity equations from which we can solve the reflection and transmission coefficients for S-polarized light. Note that these coefficients depend on the refractive indices of the two media, as well as the incident angle. Now we can do the same for P-polarization. Because in the case of P-polarization the magnetic field is tangential to the interface, it is easier to first write down the equation for continuity of the tangential magnetic field. For finding the equation for continuity of the tangential electric field, we must first express the electric field in terms of the magnetic field. So once again, we use the relation between the electric and the magnetic field. We define the magnetic field vectors, and we define the normalized wave vectors, after which we can find the electric field vectors, of which we pick out the x components to write down the equation for continuity of the electric field. The continuity equations are now written in terms of the magnetic field amplitudes, but typically, we define the reflection and transmission coefficients as ratios of electric field amplitudes. So let's use the relation between electric and magnetic field amplitudes to rewrite the continuity equations. From these equations, we can now find the reflection and transmission coefficients for P-polarized light. Let's make a quick remark about the sign convention we use. Consider the reflection coefficients for P and S-polarized light. In the case of normal incidence, there is no meaningful difference between P and S polarization. The fields will always be polarized along the interface. So you might expect that for the case of theta I is equal to 0, the reflection coefficients for P and S polarization should also be the same. However, it turns out that when you write the reflection coefficient for P polarization and compare it to the one for S polarization, they have opposite signs. How come? Remember that when deriving the reflection coefficient for S polarization, we started with the continuity equations in terms of electric field amplitudes. so the sign of the S-polarization reflection coefficient indicates the phase shift of the electric field. However, when deriving the reflection coefficient for P-polarization, we started with the continuity equations in terms of the magnetic field amplitudes, so the sign of the P-polarization reflection coefficient indicates the phase shift of the magnetic field. If the electric field undergoes no phase shift, then the magnetic field gets a minus sign, so a pi phase shift, because the sign of k hat changes after reflection. Conversely, if the electric field does get a pi phase shift, then the magnetic field does not. Therefore, in our current convention, the reflection coefficients for P-polarization and S-polarization have opposite signs in the case of normal incidence. However, one may also choose to include a minus sign in the P-polarization reflection coefficient so that the two reflection coefficients do have the same sign for normal incidence. If we choose to use such a sign convention, we can generate the following plot for the P and S reflection coefficients for an air-to-glass interface as a function of the incident angle. Note that for normal incidence, the two reflection coefficients are indeed the same. Also note that while the reflection coefficient for S-polarized light never vanishes, the reflection coefficient for P-polarized light does vanish for a certain angle of incidence. This angle is called the Brewster angle. If unpolarized light hits an interface at the Brewster angle, then none of the P-polarized component is reflected, and all that is reflected must therefore be S-polarized. So reflection at the Brewster angle converts unpolarized light to polarized light. To conclude, let's find an expression for the Brewster angle. By definition, the Brewster angle is the angle of incidence for which the reflection coefficient for P-polarization is 0. From this it follows that the numerator of the expression for the reflection coefficient must be 0. We want to have an expression that only depends on the angle of incidence, not the angle of refraction. So let's use Snell's law to eliminate the angle of refraction from the expression. We can do this by rewriting the two equations so that on the right-hand sides we only have cosine theta t and sine theta t. If we then square both equations and add them together, sine squared plus cosine squared reduces to 1, and so we have eliminated the angle of refraction from our equation. Now we can replace 1 with cosine squared theta I plus sine squared theta I and divide both sides by cosine squared theta I so that our equation only involves tangent squared theta I. Solving for the incident angle then gives us that the Brewster angle is equal to the inverse tangent of n2 over n1. Note that as opposed to the critical angle, there is always a Brewster angle regardless of whether n2 is larger or n1 is larger.